Hello students, welcome to Tuteetute. So we are discussing about the AEE examination Telangana state. Okay, so electrical question paper. So in that power system questions we will be seeing in this video. All the power system questions we will be seeing. Okay, so generally for any AEE examination or AE examination or so polytechnical lecturer examination or junior engineer examination, SSC junior engineer examination or sub engineer examination, similar model of questions will be coming. Okay, so that's why, so whenever you are preparing for any electrical examination, so you need to know about different kind of exam previous year questions like that, this year question papers also. Okay, so we have to refer if you are writing some other examinations. Okay, so first question from power systems. Okay, so consider the following list regarding compensation techniques in power systems. Okay, see what they have given. Reduces the Ferranti effect. Okay, let's see the other side first. Okay, series capacitor, shunt reactor, shunt capacitor, series reactor. Okay, 4 voltage compensating ones. Okay, so in voltage control unit we used to study these 4. So series inductor, series capacitor, shunt capacitor and shunt reactor. Okay, so these are the 4. Okay, so we have already seen. Okay, so these answers, so this is direct question only, there is nothing more to know. So whenever you connect a shunt capacitor, it will be acting as a power factor improvement device. Okay, so power factor improvement device. Okay, so in our classes, so what are the other applications also for this shunt capacitor we have already seen. Okay, so but so as a direct question they have asked, so it will be used for the power factor improvement device. Okay, so shunt capacitor will be used to increase the power factor, to improve the power factor. Okay, so for the B3. Okay, so these two options might correct. Okay, any one of these two. Next, shunt reactor, how it will be used? Shunt reactor. Okay, so shunt reactor, whatever we have easy. Okay, so first we need to observe those things. Okay, so shunt reactor. Okay, so see the other options. Increase power flow capability of line. Okay, so reduce the Ferranti effect. Okay, see direct answer is there. So reduce the Ferranti effect. What is Ferranti effect? So Ferranti effect is nothing but getting the over voltage at the output side. Okay, so at the receiving end side, if you get the over voltage because of no load condition or light load condition, that is nothing but Ferranti effect. Okay, so whenever you get over voltage, what you have to do? You have to reduce that over voltage to the normal voltage. Which device we have to use there? We have to use shunt reactor. Okay, for example, if you are getting low voltage, if you are getting low voltage at the receiving end side, to improve that voltage to the normal level, which device we have to use? Shunt capacitor we have to use. So see, power factor improvement device, similarly. Okay, so we can increase the voltage from low voltage to the normal voltage. Okay, so voltage profile improvement device, we can use this one for low voltages. For under voltages, voltage profile improvement device is shunt capacitor. For over voltages or for Ferranti effect controlling, we will use the shunt reactor. Okay, so for this one we can call this is Ferranti effect. Okay, so Ferranti, okay, so effect control device, otherwise Ferranti effect reducing device. Okay, so Ferranti effect controlling device. Okay, so controlling device we can call. See, there are different options for this one. Okay, instead of giving reduces the Ferranti effect, they can give reduces the over voltages to the normal voltages. That option also they can give. Okay, so whenever you are reading some question, what you have to do is, okay, see, reading this understanding the previous year questions is more important. Why means directly. Okay, so after 1 or 2 minutes everybody can answer these things, but whatever explanation we are giving here, okay, so that will be useful for your upcoming examinations. Okay, so not only this exam, previously completed NPDCL examination, previously completed SPDCL examination, sub-engineer examination, like previously 4 or 5 examinations we have to consider. So the trend of questions. Okay, so which area they are concentrating, like from the power systems, definitely there will be question from this voltage control unit. Okay, and similarly there will be per unit. Okay, so from the per unit system definitely one question will be there. Okay, similarly, so from the circuit breaker concepts definitely one question will be there. From the generating plants, like in 3 generating plants at least 1 or 2 questions will be coming. Okay, so generally 2 questions will come. Let's see in this question paper also how many questions came. Okay, so like that. So next, series capacitor. Whenever series capacitor, if you connect series capacitance is negative reactance minus. Okay, so this is negative reactance. Okay, so negative reactance. Whenever it is negative reactance, the net reactance will decrease. Okay, so the net reactance will decrease. So whenever electrical power output, it is nothing but EV by X into sine delta. Okay, whenever net reactance decreases, power handling capability. Okay, otherwise a steady state stability limit. Okay, so power handling capability. Okay, so power handling capability, otherwise steady state stability limit, otherwise handling of or power flow capability will be increased. Okay, so this is for the series capacitor. Okay, for the series capacitor increases power flow capability of line. Okay, so where it is series capacitor, first one C. Okay, so not that C, first one. Okay, so C first one and B3. Okay, already this is the answer. Fourth one will be the answer for this one. So anyway, remaining another one also we have to see. Whenever you connect series capacitor, series reactor, okay, or series inductor, X net will increase. Generally we don't use in our transmission lines, but in HVDC line definitely we will be using some smoothing reactor. If you see the diagram of okay, so HVDC link, okay, so bipolar you can check. Okay, so we will be using one smoothing reactor. Why it will be used? To reduce the harmonics, otherwise it will be acting as the filter. Okay, otherwise in the current, if any ripples are there, that will be reduced. Okay, so that's what so they have mentioned. Okay, so ripple current decreases. Okay, so D, what is the option? D, series reactor, D4 it is. Okay, so answer for this one is 4. Okay, so not only for that, so we can use this series reactor for the fault current limiting device. We can use as fault current limiting device also. Okay, so this is also one of the important question. Instead of giving like this reduces current ripple, they can use as, okay, see, they can use as this one. Okay, so fault current limiting device. Okay, so how we can call this one as the fault current limiting device? Whenever fault occurs, definitely high current will flow as reactance will be more in that line. So then automatically current will decrease. Okay, so how we need to know in that line we have to place the series reactor. So whichever area we are getting frequent faults, okay, so series fault, otherwise LL fault or LG fault, this type of faults are occurring, then we have to keep the reactor in that line. Okay, so series reactor we have to place. Okay, fault current limiting device. Okay, so fault current limiting device, otherwise ripple current reducing device. Okay, so like that we can answer this question. Okay, next question. In a grid connected synchronous generator working at unity power factor, increasing the field excitation has the effect of field excitation is increasing. Field excitation is increasing. So what will happen? Field excitation is increasing. Because of that, see, this is a synchronous generator. Okay, so synchronous generator it is. So whenever you increase the field excitation, what will be changing? The flux. Okay, so whatever magnetic flux entering into the system, okay, that means operating flux in the synchronous generator it will be changing, but that doesn't change the active power. Okay, so how active power will be changed? Whenever mechanical input will be increased, then active power changes will be there. Whenever excitation changes, then only so reactive power changes. Okay, so these are the basic things. Generally we don't study in our power systems, we used to study in the synchronous machines these things. Okay, so anyhow, so both subjects we need to interlink at some point. Okay, while studying the stability analysis, okay, we have to study about these concepts from the synchronous machines also. Okay, so what is the answer for this one? Increasing only the reactive power supplied to the grid. Okay, so only reactive power changes. To change the active power, what we have to change? The input, the mechanical input we have to change. Water input we have to change. Otherwise, other inputs, whatever power plant it is, that inputs we have to change. Okay. Next question. In a long transmission line operated under lightly loaded conditions, the receiving end voltage is found to be higher than the sending end voltage. Which effect accounts for the phenomenon? Okay, answer for this is Ferranti effect. Okay, so already we have discussed in the first question only. Okay, so what is the Ferranti effect? Under no load condition or light loaded condition, the receiving end side voltage is greater than sending end side voltage. That effect is called, okay, that effect is called Ferranti effect. Okay, see here only we have to know about some of the other concepts also. Okay, so I am not explaining what is the skin effect. The ability of AC current to accumulate near to the surface of the conductor. It is nothing but a skin effect. See, from this question, maximum what we can get, that we need to understand from these previous year questions. Okay, like that if you study the previous year questions, most of the times, okay, around 70% of the questions in the any examination, upcoming examinations also, okay, we can able to solve easily. Okay, so what is skin effect? You have to know. Okay, so I told already. So what is corona effect? So we have to know. Okay, so like that you study. What is proximity effect? So that also we have to know. Okay, so remember we have to read these statements once. Okay, so whenever you have this question, with this question, another 3 more concepts you are just understanding within seconds. Okay, so just to know. Okay, so if you know already these 3 definitions, that's fine. Otherwise you just know these definitions. Okay. So next, Gauss-Siedel technique is commonly used in power systems. To which of the following? Okay, so Gauss-Siedel method, so no need to even check. Okay, for the fault analysis, so what we have used? We didn't use Gauss-Siedel method. Okay, for the stability analysis, equal area criteria we have preferred. So for unit commitment, so what we have did? So we have not used these methods, right? So for what? Load flow analysis. If you have just attended the class, unit name is nothing but load flow studies. Otherwise, so load flow analysis. Okay, so that is our unit name. So and in that, so Gauss-Siedel method, Newton-Raphson method, all these things we will be studying. Okay, so directly, so this is the answer for that. Okay, so and for the stability analysis we will be using equal area criteria. Okay, for the fault analysis, so we will be preferring which bus. That is also one of the question. Okay, so that may ask frequently. Okay, so which bus will be used for the fault analysis, whether it is Z bus or Y bus. Okay, understand these type of questions also. Okay, so next, unit commitment, you know already. So this is another unit. Okay, so we used to study. Okay, so like generators. Okay, so how you will be so giving the load distribution, all these things. So generators, how they will be generating, how much percent, which generator is giving how much so power, like that. So we need to so understand this unit commitment also. Okay, so next, the surge impedance of a 300 km long overhead line is 180 ohms. For a 150 km length of the same line, the surge impedance in ohms is. Surge impedance will not be changing. How much ever, whatever be the transmission line length, the surge impedance will never change. Okay, it will be so 180 for 300 kilometers and 180 for the 150 kilometers, 180 for any other kilometers also. Surge impedance will not be. That is nothing but a characteristic impedance. Okay, so we used to call as surge impedance. Otherwise, characteristics impedance. Okay, so ZC we used to call. Okay, so these things will not change. Okay, next question, if the value of complex power flow, okay, so in a certain transmission line is assumed to be fixed. Okay, so what is fixed? Power flow. Okay, complex power flow, it is fixed. Okay, and if V donates the sending end voltage of the line, then the real power loss in the line would be. Okay, so what they are asking, real power would be proportional to. Okay, so real power, what is real power? Active power. Real power means active power. So generally how you used to give active power? I square into R. This is the general formula in any power system network. Okay, so but what they have given, they told already. So the complex power flow, it will be fixed, okay? So our certain transmission line, it assumed to be fixed, they have mentioned. So whenever it is fixed means SC is fixed. SC is fixed. How we can give S? Root 3 V I, otherwise VLIL, okay? So root 3 VLIL, like that we can give, okay? So in this one, okay, so let's take, we need relation with voltage. If you see the options, voltage relations are there. So what we need to do, so this I we will change into, so V terms, okay? So I equal to S divided by root 3V. See, this is normal formula only. So you may think, okay, why I am just writing again, okay, we have to change into this one. If the options are in I, then what we have to do, then V equal to, like that we have to write down, okay? If the options are in terms of S, then we have to change, okay? According to question only, we have to form this relation, okay? So I equal to, so S divided by, so root 3 into V, okay? So if you substitute in this one, you will get P is proportional to 1 by V I square, right? So V square you will be getting. S is constant, R is already constant, okay? R is already constant. Apparent, this S is complex power is already constant, they have mentioned, okay? So P is inversely proportional to V, okay? So answer for this question is V power minus 2, otherwise 1 by V square, okay? Next one, a synchronous generator rated 11 kV 50 MVA has a per unit impedance of 0.2 per unit on its own base. Then the impedance referred to a 22 kV 150 MVA base would be, okay? So this is definite question, okay? See, our student only already done this one, okay? So anyway, answer you will get this one. So I will tell you formula, okay? So we need to remember that formula definitely. If you don't remember also, somehow you can do this question, okay? So Z new impedance only, right? So this is impedance, okay? Per unit impedance. Z new per unit is equals to Z old per unit into MVA new divided by MVA old, okay, into KV old divided by KV new whole square, okay? So like this we have to solve, okay? Don't need to write down these things in the examination, okay? We need to get the answer. However, our student has done here, same like that, okay? Just to give what is the old value, 0.2, okay? So after that, so MV here, he has written MVA here. MVA new is 150, okay? MVA old is, okay, 50. So KV old is 11, okay? KV old is 11. So new one is 22 whole square. If you solve this one, you will be getting, that's it, okay? So once 2, so 1 by 4 you will get here, once 3, okay? So 0.2 into 1 by 4 into 3 by 1, okay? So 3 by 4 you will get 0.2 into 0.175, okay? So 0.2 into 0.75, so you will get, so 0.15, okay? So 0.15 you will be getting, okay? That is the answer. Next question, a 3-phase 33 kV oil circuit breaker is rated 1500 amperes 2000 MVA 2 seconds. The symmetrical breaking current for this breaker would be symmetrical breaking current, okay? Symmetrical breaking current, okay? So breaking current it is, okay? So breaking current, okay? Symmetrical breaking current, how we have to give? See, again, see, he has did already. So symmetrical breaking current is nothing but MVA rating divided by, okay? So MVA rating of the circuit breaker divided by root 3, okay? So root 3 into voltage value, okay? So what is the voltage they have mentioned? Otherwise we will give voltage value, okay? So 3-phase 33 kV, that is nothing but a line to line value only. So that only we have to consider, okay? So this is the answer. So MVA is nothing but 2000 MVA, okay? So 2000 in terms of kilo you will get here, because it is M and it is voltage, generally it will be in kilo, okay? So 2000 MVA divided by root 3 into, so VL value is 33 they have mentioned, okay? So if you solve this one, so in terms of kilo you will get, so what is the answer for this? So calculation only, okay? So we'll get 35 kilo amperes, okay? So like this. Next question, which of these is responsible for developing the pressure in the working fluid cycle in a thermal power plant? Okay, so working fluid cycle. Okay, so working fluid cycle means, so already, so fluid cycle means, so whatever we are sending water, feed water we will be sending, right? Okay, so who is responsible for this pressure developing? Okay, so for the pressure working fluid cycle, okay, so which cycle is responsible for the pressure development? Okay, so just see, in steam turbine, what is the use of steam turbine? It will be just converting the steam into the electricity. It will be taking the steam input and giving us, so it will, shaft will be connected to the generator. That's leave it. Okay, so but there is no conversion of anything. Okay, so it is not maintaining any of the pressures there. It is just utilizing, it is the final part, turbine. Okay, so next, superheater. What is the use of superheater? So superheater is nothing but it will maintain a little bit higher temperature of the steam. That is the application of the superheater. Condenser, what it will do? Condenser, so will send the, it will be in the condenser, whatever steam, used steam will be there, that will be converting into hot water in this one. Okay, so there is a condenser. Feed water pump, what it will be doing? Feed water pump, feed water pump is the one, so which will maintain. Okay, so at the feed water pump, the new water will be coming, otherwise cool water will be coming, and it will be joining with the hot water, so combinedly it will be again feeded to the entire boiler. Okay, so into the boiler we will be sending that. Okay, so where it will be maintaining the pressure and this temperature? So there at the feed water pump only. Okay, so here, so whatever pressure and temperature both will be maintained here. Okay, so the temperature, if it is not normal, okay, if it is not sufficient, after this feed water pump, what will be there? Okay, so there will be low pressure heater. After that, high pressure heater also will be there. Okay, so it is in the thermal power plant only. Okay, so high pressure heater, after that only, so we will be having economizer. Okay, so like that. Okay, so answer for this question is feed water pump. Okay, next question, Buchholz relay directly. Okay, so no need to see. Whenever you see this relay, okay, so where it will be used? It will be used in transformers. Okay, every year. Okay, so if 1 year 2 or 3 exams are conducting, at least in 1 or 2 exams, this model of question related to Buchholz relay or related to transformers, so this model of question will be there. Okay, a Buchholz relay is commonly used for the protection of which of the following transformer? Okay, so we can use in generators also. Okay, so in generators also we are using. So in transmission lines there are directly this type of not required. Okay, so in bus bars and transmission lines, but in the transformers you may think, okay, so which type of faults it will be recognizing means incipient faults. Okay, so incipient, okay, so incipient, okay, faults. Incipient faults means very small faults. For example, okay, I will tell you, in transformer, so windings will be there. Okay, so windings will be there. So for example, this is one winding. So if any turn to turn, okay, so between these two turns there will be some paper insulation or some insulation. Okay, so if this insulation breaks, what will happen? These two turns will become as only single turn. That means in number of turns, for example, total 1000 number of turns are there. Now it becomes only 999 turns. Okay, so that means one turn reduced means there will be a small change in voltage. So this is very small fault only, but nothing will happen to the transformer. Okay, so transformer will work properly, everything will work properly. But if you leave this fault, what will happen? It will become to the another one. It will become to the another one like this. So it will become, so totally, so 50 or 60 number of turns decreased, for example, then it will show. Okay, so reduce in voltage or increase in voltage you will be getting. Okay, according to, so it is primary or secondary side, like that. Okay, so that's why, so this model of faults, these are very small faults only, but if you leave like that, so over a period of time, okay, so like after 6 months, like that, it will become as a big fault. Okay, so this model of faults are called incipient faults. Okay, so that type of faults will be recognized by this, so Buchholz relay in transformer majorly. Okay, so in generators we are not using, okay, but we can use in the generators also. Okay, Next, which of the following could be the effect of using high speed circuit breakers in a power system? Why we need high speed circuit breakers? They have to operate within very less time. Within very less time means, why we need very less time? So whenever the generator will become, whenever fault occurs, the generator will lose the synchronism. Before losing the synchronism only, our circuit breaker has to break that line wherever fault is there. So for example, okay, so one line to ground fault occurred. Within 4 seconds, our synchronous generator will lose its synchronism. It will go to unstable region, means we have to shut down that generator. Understood, right? So before that time only we need to get operated by this circuit breaker. Our circuit breaker has to operate. This is general basic principle, right? Okay, so that's why our circuit breakers should have fast response. Okay, so that's why fast operating or high speed circuit breakers we have to use. Why? We have to make our system stability. We need to show our system stability. Because of this generator, other loads also will get disturbed, right, if it is losing the synchronism. Okay, so there will be more disturbance in the system. That's why to maintain the stability or to improve the stability of the system, we need to use the high speed circuit breakers. Otherwise, perfectly, okay, so to improve transient stability, that means in very less time. Okay, whenever fault occurs, okay, otherwise whenever disturbance occurs, immediately after that time it is called transient time. Okay, so in circuits we used to discuss about that. Okay, so after long time, that is again stable time only, that is steady state. So whenever fault occurs or whenever switch closes, okay, whenever, so there will be some disturbance immediate that time, okay, it will be called as a transient time or transient period. Okay, so to improve that transient period stability, we need to have high speed circuit breakers. Okay, so transient stability. Okay, answer for this is second one. Okay, so first option, let's see, increase short circuit current. Okay, so why you need to increase the short circuit current? Should have high short circuit current. Whenever higher short circuit current is there, then automatically so windings will be burning. Okay, so perfect wrong answer. Okay, reduces short circuit current. We have to reduce short circuit current, but that doesn't mean, okay, so fault already occurred, right? So we cannot control this short circuit current reduction. Okay, so reduce the system reliability. We need highly reliable system. For example, if not this generator, if generators loses its synchronism, some other generators also connected to the power grid. Okay, so that's why, so even one generator doesn't make much sense, but other generator also feels that burden. Okay, that much load, if it cannot manage, then automatically reliability will reduce. Okay, so that's why for the reliable system, okay, so we used to have ring main distribution system, right? In distribution we used to have this. Okay, so to have the higher reliability, okay, of the distribution system, we need to connect in ring main system. Okay, so there it will be more useful, but here so there is no much, because so our power grid or bus bar, okay, so bigger bus bar it is, so it will be always stable. That's why we used to call as a infinite bus bar. Okay, so answer for this question is improved system stability, transient stability or system stability. Okay, consider the following statements made about sequence impedances of power system components. Okay, so let's read the statements. A fully transposed transmission line has equal positive and negative sequence impedances. Okay, so transmission line, they said, so that is equal only. Okay, so for the transmission line, okay, so they have mentioned equal positive and equal negative sequence components. That is correct only. Okay, next one, the negative sequence impedance of a synchronous generator is usually smaller than, okay, so negative sequence, okay, smaller than the positive sequence impedance. Okay, so for which one they have mentioned? Synchronous generator. Okay, for the synchronous generator, x naught, okay, so generally so it will be smaller for the, okay, 1 minute. So for the synchronous generator, so we used to have the relation. Okay, so relation is nothing but, so x1 is almost equal to x2. Okay, so then x naught is less than, okay, compared to other two. Okay, so this is the one for the synchronous generator. Okay, so let me write down. synchronous generator. This is the relation, okay, of sequence impedances for fully transposed transmission line has equal positive and negative sequence impedances. This is correct only. So, but I will extend this one for the transmission line, okay. For the transmission line, x1 is equals to x2 and it will be so generally less than, okay, so 3 times less than, otherwise directly we can write down like this, okay. So next one, the negative sequence impedance of a transformer is generally much higher than the positive sequence impedance, okay. So it is not equal, greater than it is, okay. So that's it. So the negative sequence impedance of a transformer is generally much higher than the positive sequence. Remember, for the transformer, so x1 is equals to x2 is equals to x0. All the sequence impedances or sequence reactances are same only. So what they have given, the negative sequence impedance of a transformer is generally much higher, they have mentioned. This statement is wrong, okay. Only A and B are correct. Only A and B are correct. Okay, so option 2 is correct. Okay. So these are the power system questions, okay. So generally, okay, so all these question paper, whatever we got, so from this we have discussed, okay, some of the subjects, remaining subjects also we will be uploading very soon, okay. So we used to have all the questions, okay, discussion, so we will not miss any of the question. So all the question discussions we will be doing with explanations, with all the related concepts also we will be explaining in these videos, okay. So anyway, all the best. If you need any of the doubt clarification or for your guidance or for the coaching, okay, you can call our numbers, okay. Thank you so much.